Hello, welcome to Engineering Mechanics Statics. My name is Jason. I'll be your teacher and your host in this set of lessons where we will be learning about all the detailed topics and problem-solving techniques when we talk about engineering mechanics in the topic of statics. And so what we're trying to do here is, no matter what you're studying, if you're a student of math or science or especially engineering, at some point you'll be having to take a course in engineering mechanics. So no matter if you're electrical engineering or chemical or civil, or if you're a physics major or something else, in general you'll have to end up learning mechanics at some point. And I'm assuming that everyone that's watched this course has probably taken a course in physics at some point, Physics 1, Physics 2. And so in those courses we learn a little bit about mechanics, about what we call the topic of mechanics, but in this course here we're going to be expanding upon that and going much deeper and really sharpening our skills to solve a great many different types of problems. Now, the topic of mechanics, engineering mechanics, is broadly classified in two ways. All right, the first one, or the first type of problem that we'll be learning about, is what this course is about, and it's called statics, the topic of engineering statics. Now, the word static means it doesn't change, right? And so when we talk about engineering statics, we're generally going to be studying the mechanics of systems that don't really move. But we really want to understand the forces and the torques and things that we'll be talking about a little bit later, but we're studying systems that generally don't move. So you might say, well, why do we care about things that don't move? Why do we care about studying the forces inside of systems that don't really move? And a good example of that would be, for instance, building a bridge. So bridges generally have a road, and there's some kind of support structure either underneath the road or perhaps some kind of cable suspension, like the Golden Gate Bridge or some other bridges that have suspension cables. Or we could have cross members, like metal cross members that go like some sort of grid above the roadway to help support the structure in that way as well. So obviously bridges are designed to not break, to not move. They want them to be immobile and strong. But we still have to analyze how to build the thing. How thick do we need to make the support structure? How strong do we need to make the roadway? What's the spacing between the cross members to support the road? So the bridge really shouldn't move, but somebody has to calculate how to build the thing and how to analyze. When I say calculate how to build it, what I mean is we need to understand the forces in all of the support members and all of the structure, even though the thing doesn't move. So that's what engineering statics is about, or engineering mechanics statics. That's basically studying things that have forces and things, but they're generally not moving anywhere. And so that's what we're studying in this set of lessons, and also in several volumes to come. We'll be drilling down into those detailed topics, and we'll be teaching everything with step-by-step example problems. Now that's statics. The other broad topic within mechanics is called dynamics. Now the word dynamic means things are changing, things are moving, right? That's what a dynamic situation is something that's changing, right? So in dynamics, which is something we'll study and talk about in future courses, dynamics, things are changing. You may have something in motion, something rotating, something spinning, something moving. So that's the two broad classifications of mechanics topics, engineering mechanics topics. Statics, where things don't move, that's what we're studying now. Mechanics of dynamics is when things are moving. All right. Now, what are your prerequisites in order to do well in this class or to understand what I'm about to teach you? Really, you need to understand algebra. You need to have a good understanding of algebra. You need to know how to solve equations and things like that. And also, you need to have a very good understanding of trigonometry. So if angles scare you, or if you're unfamiliar with sine and cosine and tangent, then you need to probably stop here and go review some trigonometry with my tutorials, because it really makes things a lot easier. Now, I am going to give you a review of a lot of the stuff as we go, so I'll kind of guide you by the hand, but you still need to have some skills of your own bringing to the table here. All right, now what are we going to do in this lesson? We're going to start off by just doing a little bit of a review of some things that I know that you've seen before, because I'm assuming also that everyone watching this has probably taken a course in physics, Physics 1. A lot of Physics 1 is basically what we're going to study in mechanics. It's just here in this course we're going to drill down deeper into more complicated problems. So one of the first things you learn in physics or in mechanics, or something that we want to talk about, just make sure to refresh your memory, is Newton's laws of motion, right? We're not going to talk about this too much because I'll teach you what you need to know as we go on, but as you remember, there's three Newton laws of motion, three laws of motion that Isaac Newton came up with. And I'm not going to write it all out because I know you've seen it before, but you can sum up Newton's laws of motion, the first law of motion, in one word, and that's inertia. The concept of inertia. You probably heard of it as an object in rest tends to stay at rest. An object in motion tends to stay in motion. That's what the first law, Newton's first law is. And I could have written those two sentences there, and that would be the first law of motion. That's what you would probably see in a physics textbook. But I like to sum it up as one word, and that's inertia. So if I take this pen here, and if I just basically place it here on a table, right, and just leave it alone, and if we don't push on it, if we don't touch it or breathe on it, or if there's no earthquakes or anything, that pen should stay exactly where we put it. So an object in rest will stay in rest unless it's acted upon by an outside force, which means if I push it, it moves. But if I don't, then it's going to stay exactly where I put it. And along with that, an object in motion stays in motion. So when you go to the bowling alley and you roll a ball, right, the ball is going to continue rolling forever and ever unless it's acted upon by an outside force. Now, an outside force could be hitting the back wall of the bowling alley. That's going to stop it. Or could be friction with the floor. That could stop it. But if we go into space and if I throw a baseball and there's nothing at all in space, then we expect the ball to continue going on and on forever and ever. And so that's the concept of inertia. It applies to things whether they're in motion or not. That's Newton's first law of motion. There's not much else to say about it other than that. Now we have the second law of motion, Newton's second law of motion, which can be summarized by something I know everybody watching this has seen, and that is the force is equal to the mass times the acceleration, right? So what I mean by that, when I write this equation, what I'm basically saying is that if I have some mass, let's call it a ball, has a mass m, okay? Obviously, if I let it sit there, it's not going to move because I haven't pushed it. But if I exert a force on it and I push it this way with some force F, that's this force here, this is the mass of the ball, then we expect this ball to respond by moving this way, but not only moving that way, we expect it to accelerate, which means to speed up. All right? So this A goes this direction, right? So you see the red equation gives us a red acceleration. The input here is a force that we push with. We have a certain mass. Of course, if the mass goes higher and lower, we can use the equation to calculate how much acceleration we'll get or how much force we need to move that thing. That's Newton's second law of motion. We're going to spend quite a bit of time eventually in mechanics using F equals ma in all of its glory for a great many number of problems there. So it should be something you're familiar with. And the third thing we want to talk about, or the third law of motion, Newton's third law of motion, is for every action there's an equal and opposite reaction. So I'll just call it action, reaction. I know you've all heard of these laws. For every action there's an equal and opposite reaction. And what that basically means is, let's say I have a wall here. Right, so this is like a brick wall, and here's open air on this side, and over here is basically a brick wall, and here's the boundary of the brick wall. We're looking at it from the side, okay? Now if I take a ball, like this one here, for instance, if I throw it towards the wall, eventually it will make contact with the wall. So let me go ahead and draw that right here, something like this. It might get squished or whatever, but we expect it to make contact with the wall, all right? And at the moment of contact, whenever it's going in like this, we expect the ball to exert some kind of force on that wall. When you think about it, because if you throw, eventually the ball is going to smack into the wall, and as it does that, it's going to be pushing on the wall, right? Now for every action force, we call that an action force, that's what is actively happening, there's an equal and opposite reaction. So we expect there to be a reaction force of the same length as the same magnitude, but pointed in the opposite direction. So what this means is that the ball pushes on the wall, and at that exact moment, the wall pushes back on the ball. Action, reaction. So if you look at this board, right, I put my hand on the board and I start pushing on it, well, the board is going to push back on my hand. If it didn't push back on my hand, then my hand would go straight through the wall. Something's got to be pushing back. So you might say, I remember when I learned this, the first thing I was, what's pushing back? There's no other hand over there pushing back. Well, what's pushing back? Well, you know, this board here is made of atoms, and they're arranged in a solid. That's because it's a solid board. It's not a liquid. It's not a gas. It's a solid. So they're bound together, right? And so when I push, there's like an elastic force. You know, think about a tree. When you bend a tree branch, it's trying to spring back against it. That comes from the atomic forces inside. All right, so when I push on this, it's almost like a little spring that's trying to push back because of the atomic forces or the molecular forces inside. So it's almost like you can think of it as like a rubber band. When you pull on a rubber band, the rubber band's trying to pull back. That's basically because of the atoms inside there. So these are Newton's laws of motion. Inertia is an object in rest stays at rest, an object in motion will stay in motion. The second law is force equals mass times acceleration on any body. And the third law is when you push on something, you expect it to push back. That's equal and opposite reaction. Now the last thing I'll say is something that I think you've all used in physics at some point or another, but just to remind you, we have what we call the weight of an object. Okay? And so, for instance, if we have some kind of block with mass m, right, and it's sitting here in Earth's gravitational field, we know it's going to have some kind of weight. So we represent that as an arrow going down, and we say that the weight of this object is equal to the mass times gravity, where gravity is Earth's gravity. Obviously, if we go to Jupiter, this constant we call gravity is going to be stronger. If we go to the moon, gravity is weaker, so this g, this is a constant, is going to be weaker. But on Earth, it has a very specific number that we take to use in our calculations. And we'll get into the details of what it is a little bit later, but basically weight is equal to mass times gravity. I just want to remind you of that. It kind of seems to go along with Newton's laws a little bit there. In any case, it's going to be a little while before we work problems that deal with weight, but I just wanted to remind you. So this lesson has really, we haven't solved any problems yet, but we're just kind of getting our feet wet. We're talked a little bit about what mechanics is, the difference between statics and dynamics. We're focusing from now on exclusively in statics, which is the study of things that don't really move, but we need to analyze the forces. And so there's a lot of groundwork we need to lay to do that. All right, we talked about Newton's laws of motion. Most engineering mechanics books give you a little review of that in the beginning, along with the weight of an object. And then what we'll do in the next section is we'll start to talk a little about units. What units of measure are we going to work with in mechanics here? And then we'll start tiptoeing our way into vectors and how to add vectors and how to represent vectors, and we'll do a lot of work with a lot of practical problems. The trick to mechanics, I'm going to tell you right now, is practice. You really just cannot watch a video and master a topic. You need to practice it. So what I suggest that you do is watch these lessons, make sure that you understand how I'm solving everything, and then work the same problems I'm working on your own sheet of paper even after you've seen them. That's okay. I mean, even if you've watched me work it, that's okay. When you have a blank sheet of paper and you work it yourself, you're teaching yourself the material and you're getting confidence in yourself. And then when you're done with that, go open whatever textbook you happen to be using and solve additional problems. So work with me as a tutor slash lecturer, solve my problems, solve your book's problems, and you will definitely master engineering mechanics. It's all very understandable, but we do have to take our time, step by step, moving through every topic and building your skills along the way. So join me on this journey, follow me on to the next lesson in engineering mechanics, statics.